Ya-Juan Zheng, Ya-Juan, to give our theory seminar today. Dr. Zheng received her PhD from Shandong Daxue in Jinan under Professor 中国四中国老师. But she had also worked with Ma Boqiang and also Xing Zhizhong, so pretty well connected. Actually, because she's so quiet, I only learned, unfortunately, today that she has worked a lot on neutrino physics. Of course, I'm not in neutrino physics, but I did not know before. But she's somewhat more interested in collider physics, which, of course, I would like to emphasize very much because of our CMS effort. Now, I'm also in favor of linear collider in Japan. So I think we have a very nice talk today. Nice subject, searching for extra Higgs bosons at the linear collider at ILC after LHC, but that looks like a very long time from now. But we'll hear from it. Okay, Ya-Juan, please.
Okay, thanks for the introduction. Today I will talk about my recent work in progress, search for actual Higgs bosons at ILC after LHC. This is a work in progress with my collaborators from University of Taiwan in Japan. This is the outline of my talk. First is the motivation of our work. Second is we will give a brief introduction on actual Higgs bosons within two Higgs model. Then I did some research and I will show it here on the hadron collider rate for the two Higgs model particles. Then I will show you the main results on our complementary study of the actual Higgs bosons at ILC. Finally, is the summary. First is the motivation of our work. We know that the standard model has only one Higgs doublet in its Higgs sector. But if we think that the standard model electric theory is non-minimal, then it is natural to introduce another Higgs sector by extend another Higgs doublet by extend the Higgs sector. We know that LHC discovery potential for actual Higgs bosons is limited in the small tangent beta region, which I will show you later. So that's why we want to see
but what real motivation do we have for the small tangent beta region?
In the extended Higgs, in a theory with extended Higgs theory.
But you have small tangent beta, then you need very large, disproportional Yukawa coupling, right? Because I think it's okay, but just saying the huge argument says large tangent beta is favored because of NTU-Van-B ratio. So tangent beta order unity is therefore still okay. That's like the standard model. But if you have tangent beta small, then you have a problem of reversing the TB ratio, and you may have a Yukawa coupling problem. So I was asking a question in that direction. Any answer?
I see. But I think at least in all the parameter regions it's necessary for the different types of Yukawa couplings, both in small tangent beta region and also in large tangent beta region. Because even some extended Higgs sector, maybe the Yukawa couplings are not even good motivated, but it's necessary to study all the possibilities. I think.
Excuse me, that statement is assuming some particular Higgs doublet model, like type 1 and type 2 or something.
Yes, I will show you later. That study includes both type 2 and type X, and with specific types of Higgs decays. I will show you in the following discussions.
Type 2 and X.
Yes. Okay, we know that this is the standard model particle content. They have the fundamental quarks and leptons, and also the forces are interactions by the Higgs bosons. And there's only one Higgs boson in the standard model part. It is satisfied the Higgs group's symmetry of SU3 color and SU2 and attempt U1Y. So there's only one complex Higgs doublet in this standard model theory. After the electric symmetry breaking, the masses of the Higgs will give the masses of Higgs bosons and fermions. But this is the current status of Higgs searches at LHC. This is not this is the result of the spring from Atlas and the CMS. We can see that the combined muon here for Atlas 1.3 and at CMS at 0.8. Well, last week Atlas updated their results, and this is a slide taken from their seminar. They give some introductions, summaries on the present status of Higgs and its masses and its spin and CP properties, and also the different signal strings from Atlas and CMS. And yesterday, CMS also updated their recent results, gives the information of spin and property, and also the mu of the signal strings. The most important part they updated is from the Higgs to fermion coupling is updated from this H2BB, H2 tau updated from this, and with a combined result at 4.2 sigma, 4.0 sigma observed. Well, if we still can ask question that if the Higgs boson is not standard model and all it belongs to a larger Higgs sector, then we can have motivation to study the extended Higgs sector with series. For example, 2HW model with different types, and also SUSY series, which 2 Higgs doublets is naturally considered, and also the left-right symmetric model. Here, in our study, we will focus on the 2 Higgs doublet model. Let's see briefly review the history of the 2 Higgs doublet extensions of standard model. First, the 2 Higgs doublet model idea was first proposed in this paper. It is because of an attempt to find a new source of CP violation. Then it is also mentioned in this paper because to avoid the neutral Higgs-mediated two-level fluid changing neutral current, all fermions of the given electric charge can couple to at most one Higgs doublet. This impose some constraints on the 2 Higgs doublet models. And then in this paper in 1978, the parameters of the Higgs potential had to lie in a property region of parameter space to ensure that the U1 electromagnetic symmetry is not broken. And also there are important cornerstones for the 2 Higgs doublet extensions of standard model. For example, the consequent mechanism also search for the study the possibility of the action and the CP out scalar of the 2 Higgs doublet model. And also in the minimal supersymmetric standard model, the requirement of a second Higgs doublet is naturally included. Let's see the 2 Higgs doublet model particle content. By introducing another Higgs doublet, the 2 Higgs doublet fields can be written in this way. The general potential is also can be naturally written. For review, you can find in this recent paper with a heavy charge 1 Higgs doublet. After spontaneous symmetry breaking, there will be 5 physical Higgs scalar left, with 2 CP-even neutral Higgs, 1 CP-odd neutral Higgs, and 2 checked Higgs. By introducing extra Higgs doublet, some basic experimental constraints had to be satisfied. First is the row parameter constraints. From the experimental set, it is near to unity. Well, within the introduction of an extra Higgs doublet, it has to satisfy this constraints at the tree level. In the standard model, custodial symmetry exists in the kinetic term, but if we introduce extra doublet or singlet, it is also naturally exists in the kinetic terms. Another constraint from experiment is the fluid changing neutral current. In the standard model, this FCNC is suppressed by electromagnetic gauge symmetry and also the GMM mechanisms. But if we introduce the 2 Higgs doublet model, then the Yukawa matrices of the more than 2 Higgs doublets cannot be diagonalized at the same time. So we have to impose, for example, a discrete Z2 symmetry to suppress the fluid changing neutral current at tree level. Then we see that the general Lagrangian of Yukawa couplings of Higgs to fermions can be written in this way. The first line is for the neutral Higgs coupling to the standard model fermions. The second line is for the checked Higgs. And the coupling here is with different neutral or checked Higgs to different fermions listed in this table. There are in all 4 types of Yukawa couplings with softly broken Z2 symmetry. The mixing factors can be written here, and we name it as type 1 to XY. Type 1 is also called fermion phobic, and type 2 is similar to the MSSM type 2 Higgs doublet model. For the type X Yukawa coupling, in the small tangent beta region, it is leptophobic, and in large tangent beta region, it is also called leptophilic. Well, for the type Y Yukawa couplings, it has no very good theoretical motivation, but a possibility for considering the completeness of these Yukawa couplings. And in this table, the CS here represents the cosine and sine function of these mixing angles, and V is the vacuum expansion value defined from V1 and V2 of the 2 Higgs doublets. It is 246 GeV, and beta is the valve ratio of the 2 Higgs doublets. Saying beta minus alpha is defined to equal to 1. It's defined in that way so that when it is equal to 1, it will be come back to the standard model case.
Wait, can you explain again the small tangent beta? Because your lines are overmerged. Which is the small tangent beta picture?
We cannot see it. You mean the type X?
The small tangent beta is associated with leptophilic or the completeness? That's my more elementary question.
Type X or type Y?
Type X. That is the small tangent beta.
So it's the same thing. Just saying it's still type X.
Oh yes, this
with small tangent beta is leptophilic, phobic.
Yes. This for the category of type X.
Okay.
Then I will introduce the present experimental constraints from flavor physics and collider physics on the particles of 2 Higgs doublet model. First is the flavor constraints on the checked Higgs boson. This is the latest constraints of flavor experiments from these different experiments on the charge Higgs constraints. It was categorized by type 1 to XY related to my last slides. We know that since type 2 is well motivated and it is mostly discussed, so it is also mostly constrained comparing with other types. But in type 2 and type Y, we can see that there are still rooms for the large Higgs mass region when Higgs mass greater than 400 GeV, for example. Well, there's another experimental report from Baba that they observe a 3.4 sigma deviation from the B to D tau nu and D star tau nu, and it has it says from standard model, and also from their results it is inconsistent with type 2 2-gigabit model at the very large confidence level. Well, since it is not confirmed by the Bell, and also it cannot, at least for now, not have a good explanation for the excess, and so it's up to you to decide about these constraints. And then we come to the collider constraints on the charge Higgs boson. From the Atlas report, we found that they have the constraints from the charge Higgs production in these 3 different channels, and both with charge Higgs decay to tau nu, and so the final state will be the B tau jets plus tau plus jets and final state, and their results shows that in the this is the charge Higgs mass region below the top quark mass, so the top quark can decay to charge Higgs, and in this small in this small charge Higgs mass region, it's almost excluded, and only a very small region is allowed. For the charge Higgs mass above the top quark mass, the bound is less stringent, and we can still have some parameter space for the larger tiny beta region, and also the larger the better the charge Higgs mass. Also, the CMS have similar searches at light Higgs region and give the similar constraints. Now we see the collider constraints on the neutral Higgs boson. This is results from the CMS searches. The left panel is for the PP to neutral Higgs production with neutral Higgs decay to tau tau, and mainly from the gluon with a triangle loop from top, and with Higgs production. From this channel, it's the allowed region is here in the white part. We can see that it's also in small tiny beta region. This green part is excluded by the is from left constraints, and this part is from the CMS. We can see that only this larger tiny beta greater than 200 GeV, and with the tiny beta not too small and not too large region allowed. And also with tiny beta below 1, there's still small regions for tiny beta from 300 to 1 TeV. This constraint is also from CMS search, but it's for a different channel of neutral Higgs production and decay. It is neutral Higgs production in association with B quark, and also neutral Higgs decays to BB bar. It is mainly the bottom blue fusion channel. So this is also the search for the MSSM type. From these constraints, they also combined the Taiwan and lab constraints for the same channel. The allowed region here is much smaller, with 10 beta less than 20 or 30, and for small tight Higgs mass, neutral Higgs mass region.
Excuse me, why the right hand is type Y?
This search is from the type 2, but it can be it can be also used to the type Y case.
So it's not fermionic coupling, Euclid coupling is not relevant here.
You mean the?
I mean the Higgs sector of the MSSM is type 2, so I'm just wondering why type Y is relevant.
Because here the decay of the coupling of H2BB is very similar to the type Y, type 2 and type Y. I will show you later the decay branching ratio of neutral X2BB, and they have a difference of 2.
This does not touch leptons, so they are not different. The difference between type 2 and type Y is in the lepton sector, right?
Yes.
So that's the simple answer.
Yes.
So here you cannot apply to, but it's not sensitive to type Y here.
Yes, because it's it choose neutral X decay to tau.
But I think when okay, right.
There are also theoretical constraints from, for example, vacuum stability. From the 2 Higgs model scalar potential, there are 8 parameters m1 to 3, lambda 1 to 5. It can be rewritten in these 8 more physical parameters with 4 Higgs mass, 2 mixing angle, the value of the Higgs, and also the softly breaking scale of discrete symmetry, and which is explicitly written in this way. Then the lambda 1 and lambda 5 can be rewritten in these 8 parameters from the vacuum stability bounds deduced in this paper, that the lambda 1, lambda 2, and 2, 5 has to satisfy these relations. Then from this, we can give some bounds on these parameters of Higgs mass and the mixing angle. Another constraint from theoretical part is the unitarity bounds. We know that the eigenvalues of these are the eigenvalues of S matrix of 2-body elastic scattering of Higgs bosons and longitudinal weak gate bosons. And the unitarity constraints from these papers, we can see the unitarity constraints require this eigenvalues has to be perturbative, so the eigenvalues has to be less than the absolute value of this AI has to be less than 1 over 2, and the detailed deduction can be found in these papers. From the so this is the combined the vacuum stability constraints and unitarity constraints from the previous equations. It can be illustrated in the left part. It is the y-axis is the Higgs mass, and the x-axis is the 10 beta value. We choose the different deviations of sine beta minus alpha squared equal to 1. For these different curves, the sine beta minus alpha squared value is 0.995 to 0.9 with more and more large deviations from 1. So with deviations larger, the allowed region is here, like the allowed region will be smaller. And generally this, the left and the right is generally from the vacuum stability, and this is from the unitarity bound. Well, this is the right part figure is for a different illustration, but the meaning is the same. Only we with axis and x and y changed. We can see that then at with the curves drawn in this way, the other region is at here, and the Higgs mass is chosen to be different values as 150, 200, 300, and 500. So with Higgs mass larger, the allowed region will be smaller. Here we assume the neutral Higgs mass should be 226, and no mass difference between others. Combined all the theoretical bounds here. These are the figures from a recent ILC white paper, and for type 2 Higgs W model study and type X 2 Higgs W model study, for this part, this is the y-axis is the neutral Higgs mass. The left axis is the 10 beta. So this is I have explained this curve from theoretical bounds at previous slides, and the LHC discovery potential for such type 2 Higgs model is drawn here. So LHC is 300 inverse fintbar and LHC is 3000 inverse fintbar. This get from these channels of gluon to neutral Higgs decay to tau and also gluon to BB bar neutral Higgs decay with neutral Higgs decay to tau. Well, in this figure, it's a type X 2 Higgs model study, and also the LHC 300 fintbar inverse fintbar and LHC 3000 inverse fintbar was considered. It is generally the channel from QQ to tau plus or minus with phi 0 and with 4 tau final state. And from these two figures, we can see that if we believe the vacuum stability bound and also the results they showed here, then only in this region of small 10 beta and neutral Higgs mass from 300 GeV to 600 GeV, and also in this small 10 beta with less than 10 and Higgs mass around 300 and 600 GeV. In this region is beyond the LHC reach at 14 TeV LHC. So we want to see that if ILC has some advantages in this small 10 beta region, and if the Higgs mass is above if the Higgs mass is above 500 GeV, then its pair production rather than single production is also allowed, and it will contribute for the larger mass region. For the Higgs production channel at ILC, if the Higgs mass is if the center of mass energy is less than twice of the Higgs mass, then it's below the pair production mass threshold. The main production channel will be single production. For example, tau nu to chat Higgs and TB chat Higgs. And for the neutral Higgs, it's BB with neutral Higgs and tau with neutral Higgs. While above the mass threshold with center of mass energy greater than twice the Higgs mass, then the main production channel will be pair production. So if we consider the decays, all the chat Higgs decay modes then can be found in the final state. There are also other contributions for the E plus E minus